In this video, we're going to see two slightly trickier examples of integration by parts. The first of them is going to be this. We've got the integral of x to the 7 times the square root of this 1 plus x to the 4th dx. And I've put down here the integration by parts formula at the bottom. So we need to find a u, we need to find a dv. Now, because it's a product, the most natural first guess might have been to say, well, u is x to the 7th and dv is this square root of 1 plus x to the 4th dx business. But if you did that, well, you can take the derivative of x to the 7th and get 7x to the 6th. It'd be very hard to take the antiderivative of the square root of 1 plus x to the 4th. If you were trying to integrate just the square root of 1 plus x to the 4th, maybe you would set the inside of the square root to be sort of, say, a u and a u substitution. But you'd be missing the du. You wouldn't have a 4x cubed term. And then if I decided to go the other way around and I set my u to be the square root business, well, its derivative would have a blah to the power of minus 1/2. There'd be stuff on the bottom, and we'd just keep on getting more complicated. So what can I do? When I look at this x to the 7th, I can think that I can break that x to the 7th up. So for example, let me take the x to the 7th and write it as x to the 4th times x to the power of 3. We know that if you multiply two things with the same base, their exponents add together to become x to the 7th. Now, the reason why I do this is that if I thought about trying to tie an antiderivative to that square root of 1 plus x to the 4th, the thing that was missing was you needed a du, where the u is the inside, the 1 plus x to the 4th. You were missing, that is, an x cubed term. But when I split this up, I could say, well, look, the x cubed term is going to be part of the integrating out of the square root business. That leaves behind an x to the 4th. That can be my u, where now I'm talking about the u in integration by parts. So let's do that. Let's set my u to be the x to the 4th, and my dv is everything else that remains, the x cubed, the square root of the 1 plus x to the 4th, and the dx. And if I go and put those up on the side here, okay, well, taking the derivative of the u is pretty straightforward. That's just going to be 4x cubed dx. Now, the integral of this dv is a little bit trickier here because this is a u substitution. So you might have to go off on the side and do that computation. You might have to remind yourselves how to do a u substitution. But the basic plan that I'm going to do is I'm going to go and I'm going to take the inside of this. So that's this 1 plus x to the 4th. I'm going to set that to be my u. And now I'm talking about the u of u substitution, not the u in this integration by parts formula. If you prefer, you can call it w substitution. We'll call this a w. Doesn't matter. Regardless, whatever name you give to the inside, the 1 plus x to the 4th, if I look at the things that are on the outside, the x cubed and the dx, well, that is exactly what I need except for a factor of 4. The derivative of the inside is 4x cubed dx, and I only have an x cubed dx. So when I go and do my u substitution, what I'm going to get is that my v is going to be that 1/4, because I was off by the 4. Then the square root, which is blah to the power of 1/2, becomes blah to the power of 3/2, and then you divide out by the 3/2, aka multiplying by the 2/3. And so that's going to be my antiderivative, my v. Well, now that I've done that little u substitution, I can go and figure out I've got my u here, I've got my v for the integration by parts formula. I can go and put them all in, and this is what I'm going to be getting. Now, this is some progress, but I still have one more integral that I have to do. I have to do this integral now of 1/6. That was, by the way, the 1/4 times the 2/3. And then I have this thing to the power of 3/2, and then I also have a 4x cubed floating around. Well, how do I do that? This is, again, another u substitution. So you have to remember, how do I do u substitution? I keep saying u substitution, but when I say u substitution, I don't mean the integration by parts u. It's its own thing. Maybe we'll call it w substitution. Regardless, how am I going to deal with this? Well, again, it is a blah to the power of 3/2. So let's set that to be my sort of inside, this 1 plus x to the 4th. When you take the derivative of that inside, you'd get 4x cubed. And you'll notice that that occurs right there in my integral. I have a 4x cubed. And there's a 1/6 up the front. So I can go and do this integral, and what am I going to get? The 1/6. The blah to the 3/2 goes to blah to the 5/2, divided out by 5/2, aka multiply by 2/5. And then finally, I have to remember to add the plus c because I'm doing an indefinite integral. So integration by parts did it. So I think the thing to take away from this, the sort of lesson of this example, is that don't always just go and apply integration by parts blindly where you say the thing on the left is the u and the thing on the right is my dv. You might have to break it up in a bit of a cleverer way. You might, for example, have to say, what do I need to be able to do a u substitution? I'll pull out as many x's as I need to be able to do my u substitution, and then I'm off to the races in the normal way. All right, next example. In this one, it starts pretty easy looking. E to the x times cosine of x. And when I'm thinking about what should be my u, what should be my dv, it really doesn't matter all that much. Okay, taking the derivative or the antiderivative of e to the x is just itself. Cosine, whether you take the derivative or the antiderivative, it goes to a sign. It just depends on what the minus sign is going to be. But it keeps on going between sine, cos, just with different signs as you go along. So it doesn't really matter. So how about I go and say that the u is going to be the e to the x and then my dv is going to be equal to the cos x dx. Let's run with that version of it. Off on the side, u is equal to the x, v is equal to the cos of x dx. The derivative of e to the x is just going to be e to the x dx. And the antiderivative of cosine of x dx is just going to be equal to the sine of x. So v is sine of x. And so we plug it in and we get this from the integration by parts formula. But the question is, have I made my life any better? Well, this integral that we have here, this e to the x sine of x, this is not what I immediately know how to do. In fact, this e to the x sine of x kind of looks like the beginning e to the x cosine of x in terms of its level of difficulty. So if I clean this up a little bit, let me just focus just on that e to the x sine of x. Now, it's the same kind of thing. I think I could do a integration by parts to that. So let me just try. Let's do another integration by parts just on this green stuff here and see what happens. So I'm going to go and set my u equal to e to the x. I'm going to set my dv equal to the sine of x. I'm going to go and write that down. I'm going to find my du is the e to the x dx. And my v, when I take the antiderivative, is minus cosine of x. All right. So I have that. And if I want to plug this into the integration by parts formula, so the first thing, the original e to the x sine of x, that doesn't change. That's just there. And then I subtract off, I have to put brackets around it. I subtract off this relatively big thing. That's integration by parts the second time now applied over here. Okay, this is good. Because now what I have, if I look carefully, is in this. It's a third integral, and it says e to the x cosine of x. And you might think, well, hold on, that's just as difficult as it was at the beginning. But hold on, it is exactly what we had at the beginning, in fact. Indeed, this e to the x cosine of x integral is the same thing as the e to the x cosine integral all the way back at the beginning. They're the same thing. So what we really have is this e to the x term is equal to a bunch of other stuff, and then subtracted off another e to the x term. So I'm going to move it back on the other side, and I'm going to get twice the integral of e to the x cosine x equal to this e to the x sine x plus e to the x cosine of x. And then finally, I'm going to take the 2 and I'm going to move it over. So my final answer is integral of e to the x cosine of x is 1/2 now times this e to the x sine x plus e to the x cosine of x. So those are two different examples of integration by parts. I cannot possibly exhaust all the different possibilities, but the lesson I would give to you is to just play around with things. Try an integration by parts. If it doesn't seem like it's going somewhere, try to break it up in a bit of a different way, go a step further, see what you can do. It's a little bit of an art form to try to figure out what is a good way to break out an integral to do an integration by parts. And heck, a lot of the time integration by parts isn't even the right method, but that's what we're doing and playing around with right now.